Hi students, I'm going to finish up with chapter 3, finish up looking at specific heat and take a look at phase changes as the last two topics in chapter 3. So before we get started, I want to clarify something that I mentioned in class yesterday. I want to go over how do you calculate how many joules are in 1 kilocalorie. So remember I said that we have 1 calorie is equal to 4.184 joules. If I multiply both sides by 1,000, I get 1,000 calories is equal to 4,184 joules. All I have to do is move the decimal place, replaces, right? If I replace that 1,000 with K for kilo, I get 1 kilocalorie is equal to 4,184 joules, 4,184 joules. Okay, so I wanted to clarify that before we moved on to talk about specific heat. All right, so we mentioned that specific heat is the amount of energy that it requires to change the temperature of 1 gram of a substance by 1 degree Celsius, right? So if we want to take a look at, so specific heat is about how much energy a substance will either absorb or um, release to the atmosphere, right? And so when we take a look at this equation, we see that the amount of heat that's either absorbed or released is going to be equal to the mass of that substance times the specific heat times the change in temperature. So we see here that our units for specific heat are either calories or joules per gram degree Celsius, okay? Using this equation, we could determine a number of things. We can find out the mass of a substance if we were given its temperature change and the amount of heat energy that it was absorbed. So let's say if we have Q is equal to mc delta T, well, Q is heat, M mass in grams, C is the specific heat, and here we have the change in temperature. So if I have the mass and the change in temperature, I can determine the specific heat. I'm sorry, the amount of heat lost or gained. If I have, so here I need the mass and delta T to determine Q. I could also find out the change in temperature if I had now the mass and the specific heat. So I would need the amount of heat that is absorbed or released, the mass, and the mass to determine the change in temperature. Or I can also calculate the specific heat if I know, so specific heat is going to be Q divided by M delta T. So if I have the mass and the amount of heat and the delta T, then I can determine what the specific heat is. Okay, so you can use this equation to determine a number of things. The amount of heat gained or released, the change in temperature, or we can calculate the specific heat if we have experimental values. Now, the thing that you should think about when you're doing these calculations is, am I absorbing or am I releasing energy? So absorbing or losing energy. I like to think of the system as like your bank account, right? So if you think about your bank account, when you deposit money into your bank account, you are going to increase your bank account and you're going to add money, so it's a positive change, right? If you're thinking about when you withdraw money from the bank, it is a negative change and you're losing money, right? So if you're adding money, you're having a positive change. You're losing money, it's a negative change. Same thing for heat. When you're absorbing energy, then you're going to have a positive amount of heat. If you are losing energy, then you're going to have a negative amount of heat. So whenever you're doing these problems, think about whether the heat is absorbed or heat is absorbed, then you're going to have a positive Q. If your heat is released or lost, then you're going to have a negative Q, right? And if we're thinking about changes in temperature, so if we want to say, so delta means change in, so delta T is always going to be the final minus the initial temperature, right? So if we think about if my delta T is positive, what am I doing? Am I absorbing or am I releasing heat energy? We're absorbing energy. If my delta T is negative, then what am I going to do? I'm releasing energy, right? So if I have a positive delta T, that means the temperature goes up. And if I have a negative delta T, that means my temperature goes down. All right? So you think about these things when you're figuring out these problems on do I write the heat positive or negative? And is my delta T reading properly? So you're always going to be, the change in something is always going to be the final minus the initial. So let's take a look at an example. This example says that, let's increase this a little bit. All right, hey, come back, come back. It will reduce it a little bit so that we can see it. Okay, I didn't mean to do that either. Sorry, folks. I'm gonna have to reduce again. If we can, okay. All right, so calculating heat loss. This question is saying that a patient that has 5,550 milliliters of blood, and we want to know how much heat was lost when the body temperature was changed from our T initial is 38.5 degrees Celsius, and our T final is 33.2 degrees Celsius. So that means delta T is going to be 33.2 degrees minus 38.5 degrees. That's going to give us a negative 0.5 degrees Celsius. Okay? And this problem is saying assume that blood has the same density and specific heat of water. So if I've got, if density is equal to 1.00, so for every milliliter, I've got 1 gram. So I can say that my mass of the blood is 5,500 grams. So we've calculated our delta T. Now we need to take a look at our heat equation. So the amount of heat lost or gained is going to be MC delta T, right? So all we have to do now is plug and chug. Oh, and we want to know in kilojoules, right? So let's plug and chug. 5,500 grams times, and remember we're looking for kilojoules, so we've got to use this example, a version of the specific heat, where we have 4.184 joules per gram degrees Celsius, all times negative delta T, okay? I don't have any more space, or maybe I have a little bit more space. And then, do I? 1 kilojoule over 1,000 joules, because we need kilojoules and not joules cancel, degrees Celsius cancel, and we're left with kilojoules. So our answer is, let's take a look at what we get. Okay, so we get a negative 121.963. Well, if we look at our sig figs, we've got 2 here, we've got 2 here, there's 4 here, but we've got 2 here. So our answer should be what? Negative 120 kilojoules. Does it make sense? Did we lose heat? Well, we have our temperature went down, so that gives us a negative delta T. And if we're losing heat, then our Q should also be negative, right? Let's try another problem. Let's look at the bottom problem. The answer is given, but you don't know how to get there, right? So let's do this example. This example says that you have, what is it, 560 grams? 560 grams of water. 560 grams of water. So our mass is equal to 560 grams. And the question says that water is going to cool. So the water cools from T initial, which is 67 degrees Celsius, to T final, which is 22 degrees Celsius. So our delta T is going to be 22 degrees Celsius minus 67 degrees Celsius. Remember, it's always T final minus T initial. We have a negative 45 degrees Celsius. Well, it says that it's cooling, so we should have a negative delta T. So our heat is MC delta T. Mass is 560 grams. Oh, and this question is asking in kilocalories. So I've got 560 grams, and because this is water, the specific heat is 1.00 calories over a gram per degree Celsius times our delta T, which is minus 45 degrees C. And because we need kilocalories, I'm going to say that 1,000 calories is equal to 1 kilocal, right? Do the math. I get negative 25.2 kilocalories, right? Well, our sig figs, once again, are 2, all right? The example gives an answer of 25 kilocalories, and they're just giving you an absolute value, but the correct way to do it, so if I'm saying that I'm losing 25 kilocalories, then it is assumed that it is a negative amount, right? But delta T is always going to be T final minus T initial. Always. Delta T is always T final minus T initial. Remember that. Delta T, T final minus T initial. Let's move on. Let's take a look at this clicker problem. Says that we have a 1.0 kilogram sample that absorbed. So if it's absorbing, then our Q must be positive, a positive 30.7 kilojoules, right? And T initial was 20.0 degrees Celsius, and T final is how much? T final is 630 degrees Celsius. So delta T is going to be 630 degrees Celsius minus 20 degrees Celsius is going to give us 610 degrees Celsius. It's absorbed, so we should have a positive amount. Our temperature goes up, right? But this question is asking, what is the specific heat? Well, if I have Q equals MC delta T, the C is going to be Q divided by M delta T. Now, we can use these kilojoules and kilogram amounts because the kilo will cancel out, but remember, specific heat is in calories per gram per degree Celsius. So let's just convert these to 1,000 grams and 30700 joules. So C is going to be equal to 3700 joules all over 1,000 grams times our delta T, which is 630.0 degrees Celsius. That's point zero. And the reason why we have 610.0 here is because we have one decimal place and one decimal place, so our answer should have one decimal place. So let's take a look at what our specific heat of antimony is. All right, let's fix this. This is 610, not 630.0, and we end up with 0.050327, blah, blah, blah. If we go back to our sig figs, though, we've got 3 here, we've got 4 here, so let's put 3 in our answer, and I get 0.0503, and we're in joules per gram degree Celsius. Joules per gram degree Celsius. See that? Okay. Moving on along. Now, we've been mentioning specific heat in terms of the amount of heat energy that is either absorbed or gained, right? And phase changes have to do with either absorbing or losing energy, right? So if I'm absorbing energy, I'm going to be going from a solid to a liquid to a gas. Or I can go directly from a solid to a gas. If I'm losing energy, I'm going from a gas to a liquid to a solid, or directly from a gas to a solid. And we're going to take a look at what each one of these are. If we look here, let's make our screen big. If we look here, we can see that it's a cycle. Whether we are absorbing heat, or going in this direction, or if we're losing heat going in this direction. All right, so let's take a look at each one of these terms individually and how they relate to each other. Okay, so let's take a look here. All right, melting and freezing are two opposite physical changes. Now, remember, phase changes are physical. We don't change the substance. We're just changing the state in which the substance is present in the physical realm, right? So melting and freezing are opposite changes, right? Melting, I'm going from a solid to a liquid. And if you remember from just a minute ago, that means we have a loss of energy, right? But if I'm sorry, not a loss of energy, a gain of energy, because in order to go from solid to a liquid, we have to add in energy or absorb. Whereas if we're freezing solid, then I'm gonna lose energy. So what I can say is that these two are reversible reactions, right? And melting occurs at the melting point, which is a temperature. Freezing also occurs at the freezing point, which is a temperature. And because these are two reversible reactions, that the freezing point, so the melting point temperature is going to be equal to the freezing point temperature, just by virtue of the fact that they are opposing, they're opposing phase changes. And we want to say that the process of melting and freezing is associated with the amount of heat, right? It's associated with an amount of heat. So what can we say? We can say that this heat is now called the heat of fusion, right? So it is either going to be the heat that is gained during melting or the heat that is lost during freezing. Okay, so there's an amount of heat that is either released when 1 gram of a liquid freezes at its freezing point, right? So these occur at the melting point or at the freezing point temperature. So if I'm freezing, then this heat of fusion, am I losing or gaining energy? I'm losing energy, so it's going to be a negative Q. If I am gaining energy, then it's going to be a positive Q. Okay? So for any given substance, this heat that is lost, let's put an arrow there. The heat that is lost in freezing is going to equal the heat that is lost in melting. So the heat of freezing, so the heat of fusion of freezing is equal to the opposite, well, it's equal and opposite, I'll say. So the amount lost is going to be the amount gained, right, in opposite reactions. Now, when we look at going from a liquid to a gas, when we're looking at going from a liquid to a gas, we have two processes. Evaporation occurs not at the boiling point. So let's say we have a container of water, right? And all of these are water molecules. Well, some of the water molecules at the surface can gain enough energy that they can fly away from the surface, and these now have evaporated. But notice we're not at the boiling point. There's not enough heat energy to boil the liquid, but it can evaporate, right? So that's evaporation. So if I am evaporating, this process is going to be absorbing heat energy. So we should have a positive Q, right? Now, evaporation, once again, is going from a liquid to a gas, okay? We also have boiling. Well, I want to do it like I did the last one. So let's say I have boiling, and in this process, I'm going from a liquid to a gas, right? And if I'm going from a liquid to a gas, I'm going to have a positive Q because I am absorbing energy, right? And if I'm doing what we call condensation, right? We're going from a gas to a liquid. Well, because we're losing energy, we're going to have a negative Q, right? And boiling occurs at the boiling point temperature, and condensation occurs at the same temperature as the boiling point temperature, right? And it's because vaporization and condensation are reversible processes, right? So condensation occurs at the same temperature as vaporization. It's just a matter of what direction we're going in, right? So the heat, so this requires a certain amount of heat, right? And this is called the heat of vaporization, right? So I either absorb that heat to become vapor, or I lose that same amount of heat to condense and become a liquid. All right? So the heat of vaporization is the amount of heat that is absorbed to change 1 gram of a liquid to a gas at its boiling point. Also, it's the amount of energy that's released when 1 gram of a gas changes from a liquid at from a gas to a liquid at the boiling point. Sublimation and deposition are also two opposite reactions, and sublimation is when we have a solid going directly to a gas. And we know that that has to absorb energy, and deposition is the opposite, where I have a gas going to a solid. So I'm going to lose energy, and that's going to be minus or negative amount of heat that's lost. Whereas here, I have a positive amount of heat that is absorbed. Now, this process occurs because many substances have a very low boiling point. So something like dry ice, you ever been to a Halloween party and you've got all this bubbling, smoking punch? Well, that's because they take some dry ice and they plop it into the Kool-Aid, and now we end up having this spooky, smoky Kool-Aid. And it's all because dry ice or CO2 sublimes at minus 78 degrees. It has such a very low boiling point that it never gets a chance to boil. Okay, we just go directly from from a gas to a solid. I'm sorry, deposition. No, I was talking about sublimation. So sublimation, you never really get the opportunity to boil, just go directly from a solid to a gas. Let's do 2 problems and then we'll be done with chapter 3. This question says an ice cube melts to form liquid water. The heat associated with this change is what? Well, let's think about it first off. I'm going from ice to liquid water. So that means if I'm going from ice to liquid water, that is solid to liquid. And if I'm going from a solid to a liquid, I'm going to absorb energy, positive Q. But we know that from solid to liquid, that is called melting. Well, melting and freezing deal with what? The heat of fusion. If we were talking about going from a liquid to a gas or a gas to a liquid, then that would be the heat of what? Remember, gas, we can also consider vapor. So if we're going from heat from a liquid to a gas or from a gas to a liquid, then that's the heat of vaporization that we're discussing. Okay? And our last problem. So A is vaporization and freezing. So vaporization is solid. No, it's not solid. It's liquid to gas. And freezing is from liquid to solid, so those aren't reversible. B says I'm gonna sublimate, so that's solid to gas. And condensation, that's gas to liquid, so those aren't reversible. C says deposition, which means gas. It's like depositing gas to a solid, and sublimation is solid to a gas. So these guys are reversible. But let's also look at D. Melting, I'm going from what? Solid to a liquid. And condensation, I'm going from gas to a liquid. We end up at liquid, but they're not reversible. So our answer here is C, sublimation and deposition. All right, guys, that's the rest of chapter 3. And I'm actually going to post your exam on Blackboard, and I will give you information about that in class on Monday, and I will also send you an announcement through Blackboard. See you guys soon.